The lights that are commonly known as white are designed to provide neutral illumination in a room. However, they are not truly white in color. In terms of the colors we perceive, it is not uncommon to hear warm light referred to as having a reddish tone, while cold light is said to have a bluer hue. Both warm and cold lights display a range of chromatic shades that are easily visible to the naked eye. The perception mentioned here is actually a subjective experience and serves as an indication for discussing the chromaticity of light sources. Chromaticity provides a way to measure the degree of whiteness in a light source, and in order to carry out this measurement, we rely on the concept of correlated color temperature, which is measured in Kelvin degrees. Welcome back to this video series about the use of lighting technology in the operating room. Today, we are going to delve into a fascinating and important topic, namely the correlated color temperature, CCT. But before we dive in, let's take a moment to understand what we will uncover. Throughout our discussion, we will explore two main aspects related to CCT and the system used to quantify it, to then come to define the interdependence of correlated temperature with the other quality aspects of a light source. We will attempt to analyze the effectiveness of current standards for evaluating the quality of a light source. What does chromaticity mean? To describe the chromaticity of light sources perceived as white, we rely on the correlated color temperature. In order to thoroughly discuss correlated color temperature, it is vital to first understand two basic concepts: blackbody and color space. These concepts are essential. What is the blackbody then? The blackbody is an ideal object capable of absorbing all incident electromagnetic radiation without reflecting it. We can select a blackbody as a representation of color temperature thanks to its dependence on temperature. All radiation emitted by the blackbody is solely determined by its temperature, causing it to change color as it warms up. The blackbody's temperature variation makes it a suitable candidate for illustrating color temperature changes. The second concept to be considered is that of color space. That is, a graphical representation of an abstract mathematical model that allows to describe colors by clear numerical coordinates. The calculation of the correlated color temperature is done on the basis of the emissions of a black body subjected to heat. The chromaticity coordinates that identify it at different temperatures joined. Together draw in color space a curved line called Planckian locus. Once the Planckian locus has been defined, the light from the source under examination is then compared with this line so as to establish its color temperature. According to convention, lights that have chromaticity coordinates positioned on or close to this line are classified as white. As a result, their specific color can be indicated using the corresponding blackbody temperature, expressed in kelvins. Most lights are not directly superimposed over the Planckian locus in terms of chromaticity coordinates. Instead, they are positioned on one of the isotemperature lines that intersect it. Thus, the color temperature value is determined by the temperature of the isotemperature line closest to the actual chromaticity coordinates of the light. Overall, most lights have colors that can be represented by points on the isotemperature lines rather than right on the Planckian locus. It is therefore apparent how the single value offered by color temperature alone may not be entirely representative of the chromaticity of a light. If a light source's coordinates are positioned relatively far away from the nearest point of the Planckian locus, it appears useful to consider a second element, the so-called DUV. This value represents the distance of the chromaticity of the light source under examination with respect to the nearest point on Planckian locus. The DUV will be a positive value if the light under examination will be positioned above this line, resulting in chromaticity tending to yellowish or greenish shades. On the contrary, it will be represented by a negative value if the light will be located below this line, consequently turning to pinkish or purplish shades. Conventionally, a light is therefore considered the whiter the closer its chromaticity coordinates are located compared to the coordinates of the Planckian locus. Unfortunately, achieving objectivity in defining the whiteness of a light is impossible. The literature consistently highlights this criticism, emphasizing the inherent difficulty in accurately determining the whiteness of light. So, a method for determining the whiteness of light was established. However, it has become apparent that this method is unsuitable for analyzing light sources, with the exception being the blackbody used in the original calculation. This raises the question if the correlated color temperature is not an appropriate measure for evaluating the color temperature of a light surface. Why is it still commonly employed? It continues to be used because correlated color temperature, or CCT, has a significant impact on the visual experience and comfort of the observer, especially in specific contexts such as the surgical environment, meaning places where the right illumination can prove crucial to the success of a surgical operation. It is therefore better to have an underperforming engine than to row the boat forward, I would say. The optimal color temperature value remains for the most part a subjective consideration, and its calculation an imprecise process. The only solution, therefore, is to offer the user the choice to select his preferred value of CCT independently so that they can determine the best chromaticity condition. Manufacturers of surgical lamps, being able today to exploit the peculiarities of LED technology, can offer products with an adjustable color temperature. To ensure a quality light, it is essential to adjust within the recognized optimal range of 4200 Kelvin to 4800 degrees Kelvin. This precise adjustment guarantees the desired outcome and maximizes the effectiveness of the lighting. Moving on to the second topic in this video, we must now delve into the issue of interdependence of color temperature with the other crucial elements that define the quality of a light source. Specifically, these elements are color rendering and light intensity. However, it is necessary to clarify that we will touch upon this aspect only briefly. Our aim is to inform you about its significance rather than providing an in-depth analysis. Let us therefore begin with the relationship between color rendering and color temperature. The perception of color rendering, or CRI, is affected by the color temperature. The higher the color temperature, the greater the color rendering index value required by the observer to evaluate the environment as natural and comfortable. The lower the color temperature, the lower the color rendering value required to achieve this same feeling. Taking into account the fact that the IEC 6601-241 standard requires that surgical lamps offer a color temperature between 3000 and 6700 degrees Kelvin, what has been said therefore results in the partial irrelevance of color rendering. Considering now the relationship between color, temperature, and light intensity, it is noted how the perceived brightness increases as the color temperature increases, and how it has been shown that LED lighting systems with mixed color temperature appear brighter than systems with fixed color temperature. This perhaps does not have as much relevance with operating room use, yet it allows us to demonstrate an interconnection and interdependence between these two factors. It has in fact been demonstrated how these three elements, color rendering, luminous intensity, and color temperature, are interrelated and in a certain sense interdependent aspects. Therefore, it becomes clear that when considering the quality of a light source, one must carefully analyze each of these aspects while avoiding favoring one over the others. This is because specific values in any of these aspects may lead to unfavorable situations during the usage of the lamps. Hence, it is crucial to consider all these aspects collectively and at the same time. This is precisely why the limit values defined by the relevant standards for these three areas appear to be considerably flexible. For instance, the luminous intensity ranges up to 160,000 lux. The color temperature varies between 3000 and 6700 degrees Kelvin, and the color rendering must be above 85 CRI. The hope then is that these three elements will be replaced by one single index that will enable the quality of a light source to be defined without going into too much detail about its constituent elements. A single index that would allow the limitations for color rendering, luminous intensity, and color temperature to be exceeded. Thank you for your attention, and if you are intrigued by this video, I recommend following our YouTube page to be able to go into more detail on other related topics.